Students, let's see electrophilic substitution in aromatic ethers. So, if we take an example of aromatic ether, benzene ring attached with benzene ring with alternate double single bond attached with ether functional group with alkyl group. So, this is the general example of aromatic ether. On this oxygen, two lone pair electrons are there, and that's why this alkoxy group, this alkyl group shows the positive inductive effect, means it pull away this pair of electron towards this oxygen. Then this pair of electrons shifted in between this oxygen and carbon. So what happened? So this pair of electrons shift here to complete the valency of this carbon. This pair of electron of pi bond shifted on this carbon. So what happened? This pi bonded electron shift on this carbon atom, and there is a formation of resonance structure first. So by shifting lone pair, oxygen acquire positive charge which is doubly bonded with this benzene ring. Actually aromaticity of benzene is disturbed, and here 2 pi bond remains in this benzene ring. Now it again shift in between these two carbon atom. At the same time, these 2 pi bond electrons are shifted towards the para position carbon in this benzene ring. So here we get a next resonating structure of this aromatic ether, that is oxygen doubly bonded with this double bond shifted here. This negative charge comes at para position, and we get this is the next alkoxy structure. Oxygen carry positive charge with alkyl group. So here at para position this negative charge is formed. Now this negative charge means pair of electron shift in between these two electrons. At the same time, these pi bonded electrons are shifted to the next carbon, means here O plus R doubly bonded with this 6-membered ring. Here position of double bond comes here, and at ortho position negative charge is there, and finally this negative charge shift in between these two carbons, and this pair of electron shifted back to the again towards its original position. So here we get final structure of aromatic ether is like this way: singly bonded oxygen with alternate double single bond benzene, and these are the structures formed in aromatic ether due to presence of this alkoxy group on the benzene ring. So these are the resonating structures are formed, which is possible due to this alkoxy group which is attached to this benzene ring, and this is aromatic ring is activated, and due to this alkoxy group aromatic ring is activated at ortho, para and again ortho position. So this alkoxy group is responsible for the ring activating at ortho and para position. So due to alkoxy group, OR group is responsible for the activating benzene ring, or aromatic ring is activated by this alkoxy group. Aromatic ether is a ring activating, and the benzene ring is activate at ortho and para position, and also this group is ortho and para directing. Ortho and para directing means here ortho and para directing means what happened when this pair of electron on this oxygen shifted here in between oxygen and carbon. To maintain the tetravalency of this carbon, this pi bonded electron are shipped on the ortho position. So negative charge at ortho position, positive on this oxygen. Now this pair of electrons shift in between these two carbon atoms, and to complete the valency of this carbon, shift this pi bond electron on para position. So negative charge comes at a para position. Now this is shifting between these two carbon atom, the next structure, and to maintain the valency of this carbon, this pi bonded electron shift on the ortho position. So negative charge comes at ortho position, and finally this negative charge, that is electrons, are shifted in between these two electrons to complete the valency of this carbon. This lone pair electron shifted back on the oxygen. So we get here final structure of this aromatic ether. And this in resonating structure first, second and third. This is first, second, third structure of resonance, which is formed in this aromatic ether, which is responsible for the reaction, that is a electrophilic substitution reaction. Due to this negative charge on ortho and para position, the positively charged ion gets substituted at para and ortho position. So this ortho and para directing group, and this happens due to presence of this alkyl group with oxygen, that is alkoxy group, which is a ring activating group, as well as ortho and para directing group. So what happen in case of the reaction takes place with aromatic ether? First reaction is their halogenation reaction. In this first reaction, halogenation reaction, in the halogenation reaction with bromine takes place. So let's see what happen when this anisole. So what is the formula of anisoles here? Benzene ring attached with OCH3 group. This is anisole when treated with bromine, that is Br2, in acetic acid as a solvent. So CH3COOH, acetic acid is a solvent, and in absence of this FeBr3 catalyst, this reaction takes place because of this OCH3 group. This methoxy group is attached to benzene ring. In absence of any catalyst, that is FeBr3 catalyst, ferric bromide catalyst, the reaction takes place. So how the reaction takes place? Let's see. This Br2 breakdown heterolytically. So we get here Br2. So one Br takes this both electron and form Br plus and Br minus. So this Br plus bromonium ion is substituted at ortho and para position of this anisole. So we require the mixture is formed. So to balance the equation, we require 2 molecules of anisole plus 2 molecules of Br2. In first anisole, this Br is substituted at ortho position. Here Br is there. In second anisole molecule, this Br is substituted at para position. So benzene ring attached with methoxy group, and this Br plus group substituted at ortho and para position, and one hydrogen replaced from this ortho and para position combined with remaining 2 Br. So here formation of twice HBr is the byproduct. So balanced equation. In this ortho and para bromo anisole containing para bromo anisole is the major compound. So this is the major one. Major means it is formed in the large percentage. So major compound para bromo anisole. This is the para bromo anisole is the major compound, and ortho bromo anisole is the minor one. So this is about the first reaction, halogenation. This reaction takes place due to presence of this methoxy group on the benzene ring. We get its corresponding Br orthobromoanisole and parabromoanisole. Para compounds are the major one, and this is the bromination or halogenation reaction takes place with the anisole. Second reaction is there. So second reaction, Friedel-Crafts alkylation and acylation. So Friedel-Crafts reaction. In this Friedel-Crafts reaction, there are two types of reactions are there. Alkylation and acylation reaction is there. So first we will see alkylation reaction. Alkylation reaction means alkyl group is introduced with this benzene ring. So if we take again anisole, it is takes place with the aromatic ether. So anisole benzene ring attached with OCH3 group is nothing but anisole when it is treated with alkyl halide, that is methyl chloride. The reaction takes place always in case of Friedel-Crafts. Anhydrous AlCl3 is used as a catalyst, and this anhydrous AlCl3 helps to break down of this CH3Cl group breaks heterolytically. These both bonded electrons are goes towards this Cl, and there is a formation of CH3 plus and Cl minus. So this positively charged ion gets substituted at ortho and para position of this anisole. So we required again two molecules of this alkyl halide as well as anisole. In the first molecule of anisole, this CH3 is substituted at which position? At ortho position. CH3 plus gets substituted at ortho position, and in second anisole, this CH3 group is substituted at para position, because already you know about it. In its resonating structure, negative charge is formed at ortho and para position, and that's why this electrophile, that is positively charged ion, gets substituted at ortho and para position, and the byproduct is 2Cl combined with hydrogen replaced from this both ortho and para position. So here we get the byproduct, that is twice HCl. So here again this which one is the major product? This 4-methoxytoluene is the major product. So this is the para containing compound is the major one. This 4-methoxytoluene is the major, and 2-methoxytoluene is the minor one. So para compounds are major, which are formed during the reaction. Now next one, again same reaction in Friedel-Crafts reaction, that is the acylation reaction. So B point, acylation reaction. In acylation reaction, the acyl group is introduced with the acetylation or acylation. This methoxybenzene, that is anisole. So anisole when treated with this acetyl chloride. So what is the formula of acetyl chloride? CH3COCl. So this acetyl group substituted at ortho and para position. That's why this reaction is called as a acylation reaction. It is also takes place in presence of anhydrous AlCl3. And what we get? Here also we get the mixture of two compounds. That's why to balance the reaction, we require 2 molecules of anisole plus 2 molecules of acetyl chlorides. So acetyl chloride, when treated with anisole, what happened? In one anisole, this acetyl group is substituted at its ortho position, COCH3, and in other anisole, this COCH3 acetyl group is substituted at its para position, COCH3. Now, what is the byproduct? One hydrogen replaced from ortho position and other hydrogen replaced from para position combined with these 2 molecules of Cl and form twice HCl is the byproduct. Here also this acetophenone, that is 2-methoxyacetophenone and 4-methoxyacetophenone. So 4-methoxyacetophenone is the major compound and 2-methoxyacetophenone is the minor compound. So here again we get its corresponding ortho and para directing compound due to presence of the negative charge or negative charge produced at the ortho and para position. Now next, third one more reaction is there, nitration reaction. So what is meant by nitration? You know about it. So nitration reaction means reaction takes place with nitrating mixture. So what is meant by nitrating mixture? Nitrating mixture means mixture of concentrated nitric acid and concentrated sulfuric acid. So when this anisole, that is methoxybenzene, benzene ring attached with methyl with oxygen. So this is the anisole. Anisole when treated with concentrated nitric acid, HNO3, in presence of concentrated sulfuric acid, acts as a catalyst. Sulfuric acid helps to break down of this nitric acid. The breakdown takes place like this way, OH minus and NO2 plus. So this NO2 plus is a electrophile and which is substituted at ortho and para position of this anisole. So we again required here a mixture of ortho and para. So balance the equation, we required 2 molecules of anisole plus 2 molecules of concentrated nitric acid. In one anisole, this NO2 plus gets substituted at ortho position. It is a minor product. In other anisole, this OCH3 group attached to the benzene ring, and at its para position this NO2 group is substituted. So this is the para nitroanisole is formed. So para compounds are the major one, para nitroanisole is the major one with the removal of byproduct. So what is the byproduct? See, is hydrogen from both position ortho and para position, 2 hydrogens replace and combine with this 2 OH minus. So we get here twice H2O is the byproduct. So here we get this para nitroanisole is the major compound and ortho nitroanisole is the minor compound. So like this way this anisole is converted into its corresponding mixture, that is ortho and para nitroanisole. Para compounds are major in case of this anisole. So here we complete the chemical reactions with the aromatic ether. So same way the reactions in all these anisole, the reactions are takes place at ortho and para position, because in case of its resonating structure, due to presence of methoxy group, the negative charge comes at ortho and para position, and that's why this electrophile, that is positively charged ion, gets substituted at ortho and para position. So this is about the nitration reaction. Now next part, that is the last part from this chapter, is uses of alcohols. So first we'll see uses of alcohols. So alcohols, from alcohol, this methyl alcohol is used as a solvent for paints and varnishes. First member of alcohol, methyl alcohol. Methyl alcohol, which is used as a solvent in the production of paints and varnishes. So colors are prepared by using solvent methyl alcohol, which is a solvent in paints and preparation of varnishes. Next, one most important use of the ethyl alcohol is there, C2H5OH. Ethyl alcohol is also very important alcohol which is used in sanitizer, also for in beverages also. Again, there is a most important use is it is used as a antifreeze agent. Antifreeze agent in automobile radiators. Antifreeze agent in automobile radiators. Automobile radiators means in radiators means in cold countries the fuel must be kept in liquid state. So without freezing the fuel remains in liquid state, and this is for this purpose this ethyl alcohol is added in a fuel which keeps the fuel in liquid state at a low temperature, and again it is used as a solvent for the different purposes. So these are two important uses which are very important for the objective questions also. Now next important compound from this chapter is ethers. So ethers, from ethers, first compound or the diethyl ether. Diethyl ether is used for the anesthetic purpose. Anesthetic purpose. So which anesthetic purpose. So general anesthesia in surgical operation, this diethyl ether is used for this purpose. And one more use of this ether is this diethyl ether again used as a solvent in the Grignard's reagent, as well as this first use. Second use of diethyl ether, which is used in the production of Grignard reagent. Grignard's reagents are prepared in presence of ether. So this diethyl ether used as a catalyst as a solvent, as well as it is used in the fats, waxes and oils. It is used as a solvent for the production of fats, oils and waxes. So these are some important uses of ethers. One more important compound from this chapter is phenol. So one more is compound, that is the phenols. So phenol is also used for the different purposes. One of the use is dilute phenol is used as dilute phenol, that is 0.2% phenol is used as an antiseptic. So antiseptic means to kill the microorganisms on wounds, again cuts, burns, etc. So it is which is used as a medicine on, that is to kill the microorganisms. This microorganisms, to kill microorganisms on wounds, again cuts, burns. So it is used as an antiseptic. And one more use of this phenol is it is used in the production of phenol formaldehyde resin, in the production of polymer, that is phenol formaldehyde resin. Phenol formaldehyde resin, that is the polymer, and its name is a bakelite polymer, which is prepared by using phenol. So these are some important uses of phenol. Again, this phenol is used in the production of, one more use is there, it is used in the fresheners. Room fresheners are there. In that liquids, air fresheners, room fresheners. So these fresheners content, the phenol is the most important content is there. Again, deodorants are there. In deodorants, phenol is there. Again, mouthwash. In mouthwashes are there. So in mouthwash, phenol is also there in its dilute form. Again, calamine lotions, floor cleaners, calamine lotions are there, which are also used to kill the microorganism. Again, floor cleansers are there, cleaners are there. So in all these contents, etc., in all these liquids, the phenol is used as to kill the microorganisms. So these are some uses of phenol, and here we complete the chapter alcohols, phenols and ethers.